Welcome to the Problemas channel, season 3, episode 24, the episode which I titled 3 Creative Evaluations of Ubiquitous Integrals that you see behind me written on the blackboard. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemas Channel How To. We recommend that you watch that episode in its entirety. Follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. In the mathematical problem S3E24, we're asked to evaluate the following two ubiquitous integrals in at least 3 distinct creative ways. First, we're asked to evaluate the integral whose integrand is represented as a product between the Euler's number e, or the base of the natural logarithm raised to the power ax, and the trigonometric function of cosine that is evaluated at the argument b times x. The integration is carried out over the independent variable named x. We will refer to this integral with the uppercase letter c for cosine. And we're also asked to evaluate the sibling of the first integral, whose integrand again is represented as a product between the Euler's number, or the base of the natural logarithm e raised to the power ax, and the value of the trigonometric function of sine evaluated at the argument that is represented as a product b times x. The integration is carried out over the same independent variable named x. We will refer to this integral as the uppercase letter s for sine, s for sine, c for cosine. A and b are constant real numbers, and by creative, the emphasis on creative evaluation of these integrals, we definitely do not mean the boring integration by parts, even though integration by parts is of course a viable way of evaluate these integrals. For this channel, this method is not creative enough. You will have to do better than that, and to that end, on this channel, the following 1, 2, 3 ways of evaluating the given integrals do qualify as creative. First, in the order from less intellectual voltage to more intellectual voltage, we will use the mighty technical power of complex numbers in order to evaluate the given integrals. Then, for the second way, we will construct a system of linear equations in our integrals shown on the right side of your screen. And finally, for the way number 3, we will show that, for example, actually both integrals satisfy the following homogeneous linear ordinary differential equation with constant real coefficients. It is written over here on the lower right side of your board, and as we solve this ordinary differential equation using the methods of solutions of such differential equations, we will discover that yes, it is quite possible to evaluate the given integrals by solving a differential equation instead of traditional integration as most students think of it. Before we deep dive into the underlying mathematics, two things. One, in season 3, episode 22, we showed where the integrals that we will evaluate in this episode come from. For those members of our audience who have missed this episode, we recommend that you find it and watch it, because in that episode we solve the following problem from physics. If a point is executing a planar motion or a motion in a plane in such a way that is both tangential and normal accelerations remain constant at all times, what is the shape of that point's trajectory? In the process of solving that problem, we come across these precisely integrals, and also as a side effect, we discovered that in this case, the point will trace the so-called logarithmic spiral, and the constant tangential and normal accelerations in this case become none other than the main characters of the cotangent of the angle that any radial straight line that passes through the center or through the origin of the chosen coordinate system forms with the consequent trajectory actually at any point of that trajectory. That's number one. Number two, what will unfold in the next few seconds is the classical application of the transform and conquer, TAC, transform and conquer problem solving approach. We studied this problem solving approach in depth on this channel across the following 5 episodes. Season 1, episode 3, 4, 5, 6, 7. If you joined our channel, again, like I said at the beginning of this episode, after season 1 or after season 2, we recommend that you find these episodes and work your way through, because otherwise you will be pretty thoroughly lost in what is about to transpire. And the best way to find these episodes is to download the free season 1 index file, and in that index file you will see the links to all the episodes. Click, 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 and watch, watch, watch. And here comes the crux of the matter of technical ingenuity for humans. A lot of times, pretty much all the students who are told after the fact how this or that problem is solved, the students realize that they did possess, or they do possess, the needed or the required unit of mathematical knowledge. The problem or the challenge here with the creativity and ingenuity in technical area is the following. Find a way to connect what you already know with what is needed. In other words, how is it possible to fish out the needed unit of mathematical knowledge from your personal web of mathematical knowledge that you already possess with what is required in this problem? This is an interesting question, but here we fast forward to the so-called complex numbers, and pretty much by the time students take on this type of integrals, all of them know about complex numbers, but somehow this way, that way, they fail to come up with this idea, and this idea is quite straightforward and amounts to the following. Look, b is a constant real number, x is a real number, the product of any two real numbers is a real number. Consequently, by the Euler's formula, what do we have? We have it that for all real numbers, let's write it down like this, e raised to the power I bx, we have the following. Leave some room right here. Cosine of bx plus I sine of bx. This holds for all bx real. And now if we look at the structure of our integrand for the first integral, let's say, we will have the following. We will see that we have to multiply this thing by ax, let's say from the left, all real and all complex numbers for that matter actually commute under multiplication. It doesn't really matter from which side we multiply one real number by the other. So here we will multiply this by the same factor. We'll put it like this. And what do we see now? Well, we see now that if we integrate both sides of this result, like so, then all of a sudden on the right hand side of this relation we have our integral. When we multiply out these terms, we will have on the one side our integral c, and on the other side we will have I multiplied by, like this, if I'll designate it like so, we will have the integral s. In other words, if we name as I the following thing, then we will see that once again we multiply e raised to the power ax by cosine and by sine separately. This is completely doable. The number of terms is finite. We do not have to worry about uniform convergence or any of this complexity. So if we name our integral like so, okay, we can jam in dx just to make everyone happy. Dx, then what do we see? We see that our integral c will become the real part of the integral I, and our integral s will be none other than the imaginary part of the integral I, because evidently in this case our integral I can be represented as its real component plus its imaginary component I. And now our ability to evaluate the given integral c and s hinges on our ability to integrate an equivalent. You see, this is where the transform and conquer problem solving approach comes in. We preserve the technical essence of the original problem, but we managed to transform it into something, into a setting where we do gain a competitive advantage. In other words, technically, our ability to evaluate the given integrals c and s hinges on our ability to integrate this here equivalent integral. But how can we do that? Well, we see right away that evaluating this equivalent but transformed integral is much more straightforward. What is about to transpire in the next few seconds is a standard fare in all of complex analysis, and you will see it time and time again. And this maneuver amounts to the following. We take any complex entity whatsoever, it doesn't really matter which one, as long as it is a complex entity, and we decompose it into the sum of the following two things. A function u that has only real arguments plus I multiplied by yet another function that also has only real arguments. And this decomposition of this complex entity into the following construct is usually what bears so much fruit in all the underlying computations. In other words, our ability to evaluate the given integrals, as I said, hinges on our ability to evaluate a transformed integral, and the transformed integral is actually a child's play, because in this case this doesn't work out always with complex numbers. You have to be actually extremely careful, and I will say a few words about it in a minute. But right now we use the fundamental or the basic property of complex valued exponentials, where we can collapse the product of two into one exponent, where the power of these exponents is summed together. So this will be the integral of e raised to the power x as a common factor. We carry it out, dx dx. And what do we do here? We will jam this under the differential a plus ab, and in order to compensate for the said jamming, we will multiply the whole thing by this factor 1 over a plus ab. You see, this is a standard maneuver. If you still have trouble doing this, let's say rename it into k. So you have the integral of e raised to the power kx dx. And here x is still a real quantity. So now kx, this becomes k, this becomes k. Pretty much all the good things that you used to be doing in, let's say, in high school, nothing really changes, and the game is essentially over. We now write down the result as follows. This is equal to 1 over a plus I times b times the original exponent, a plus ib x. You see, this is it. And now what we have, this is our complex quantity, the one that I portrayed with the wiggly. So the idea here right now is to decompose this complex quantity into the sum whose structure we already saw. Something, a function of nothing but real arguments plus I times yet another function of nothing but real arguments. This maneuver was used all over the place from a long time ago, several hundred years ago. For example, Euler used this to a great tactical advantage, and this is what we will do. So how do we transform this animal into the sum that we just talked about? First, we deal with the ratio over here. This is again a standard maneuver, the way we split this into a real component plus I times the imaginary component is we multiply both the numerator and the denominator of this ratio by the conjugate image of the denominator, which is a minus I times b. So this is what we write. A minus I times b divided by, let's do this over here just in case. Usually you will carry out these computations in your mind. You already know this in your sleep. You do not really have to spend any time on it, but to make sure that, because the members of our audience come from all walks of life and with different level of mathematical maturity and mathematical preparedness, this is the difference of squares. A squared minus ib squared. I squared comes out to be what? Minus 1. So this comes out to be the sum, a squared plus b squared. This maneuver, once you see it once, you will remember this for the rest of your life. You will not be spending any time on these things. This will be basically a reflex in your body from this point on. So this is what we have. A squared plus b squared. And then we again spell out this exponent here using what? Using our favorite Euler's formula, but before that we manipulate it a little bit again. We unzip it into, like this, into the exponent a times x times, let's do this, cosine of bx plus I sine bx. That maneuver should be understood by everyone, but just in case, on Quora I've seen people ask all sorts of questions. Let us be explicit and explain this once. This becomes, look at this, ax plus ibx. Still, we simply opened up the parentheses. This is a middle school maneuver, nothing yet, but then this construct can be replaced with the following one, times. So far so good. This should be understood by everyone. And then we spell out the e raised to the power ibx. This is a real number, and we seek the Euler's formula onto it. This is it. This is where this result came from. Nothing complicated. Once you understand this, again, you will not be spending any time on it. This will be another reflex in your body. So now all we have to do is carefully decompose this animal into the formation that we discussed a few seconds ago. Something real with real arguments only plus I times another something real with real arguments only. So let's do this. E to the power ax is the same all over the place. Let's count all the real terms. A in the numerator over here will be multiplied by this exponent with the denominator, of course, and the cosine of bx will be here. Next time when a is multiplied by I sine, it will belong to the imaginary part. For now, it's from the wrong side of town. We forget about it. So we write e to the power ax divided by a squared plus b squared. This is our formation over here. And what do we have first? a times a times cosine of bx. Wonderful. What else will we have? Negative ib times the cosine. I will survive. It will go towards the imaginary budget. We do not need that. We drop it for now. Next time we multiply minus ib times I sine bx. I times I minus 1. Minus 1 times 1 is plus 1. So we will have b sine bx with the plus sign plus b sine bx with a plus sign. Voila, we have our real part. This is our real part. And we already know that this is our integral. You see, this is the almost mechanical zero intellectual effort computation. And what do we do now? Plus I, we courageously put down I right away. And now we deal with the imaginary part. Look at this. With the imaginary part, we'll have what? We'll still have e raised to the power ax divided by a squared plus b squared. This is not going anywhere. This guy, they're omnipresent, always there. Now we deal with a. A will be multiplied by I times sine of bx. So this will be a times sine bx this time. You see, before a was bound to the trigonometric function of cosine. With the imaginary part, it is bound to the trigonometric function of sine. And what else will we have? Well, we will have negative ib multiplied by the cosine bx. So this constant parameter b will be bound to the cosine with the negative sign. So minus b times cosine bx, like so. And what is this? Well, this is our imaginary part, and we already know that this is our integral s. Before moving on to the next creative way of evaluating the given integrals, try to answer the following question correctly and on your own. And what just transpired? What was the mathematics or mathematics with the capital M, and what was not mathematics with the capital M? The correct answer to that question is the following. In what just transpired, the mathematics or mathematics with a capital M was the process of generating the idea of bringing in the tactical might of the complex numbers in general and using the Euler's formula in particular, and everything else that followed that idea was not mathematics, because once that idea was generated, that idea cranked out the results shown on the board in front of you mechanically with zero intellectual effort. In other words, the process of generating an idea or searching for a fruitful idea is the mathematics or mathematics with a capital M, and what follows is basically computational calisthenics. We did not really act on the capacity of mathematically inclined thinkers when we computed a trivial baby integral and then split that integral into two parts, the real part and the imaginary part. I will not go over the details of what you see, the formulas that are written on the board in front of you or deduced in a public fashion. Hopefully you followed every step, but I will just say that our indefinite integral over the trigonometric function of cosine is shown on the top of the board with the constant of integration discriminated by the subscript c for cosine, because we have two indefinite integrals in one location, and in order to be pedantic, we distinguish the two constants of integration just to make sure that they are different. And on the bottom over here is the second line. We show the result for the indefinite integration over the trigonometric function of sine. This is our result plus the constant of integration discriminated with the subscript s for sine. Of note over here again is the following. We have the factor of e, the Euler's number, raised to the power ax in both cases, multiplied by the following ratio shown over here. In the denominator we have a squared plus b squared in all cases, but in the numerator we have different constants, or let's say the same constants a and b bound to different trigonometric functions. And the moment we have these results on the books, we can instantly manufacture the corresponding results for the improper convergent integrals, and in order to make sure that our improper integrals over the following infinite integration domain from 0 to positive infinity converge, we demand that our b real number, that is a constant, can be actually anything, but the constant real number a must be strictly positive greater than 0, and in these integrals here, here, and here, and here, we'll have to put the minus sign in front of a. Which means that in our mind's eye, or mentally in the formulas shown on the top and in the middle, we replace a with minus a, minus a, minus a. Here no a, minus a squared, no matter. Here a becomes minus a, and here a minus a squared does not matter. And we obtain the following results. The independent integration variable here, in this case, in the result, disappears. We take the limit at the upper boundary, we take the limit of the corresponding results when x tends to positive infinity or grows without bound. At the lower integration boundary, the trigonometric function of sine vanishes, so gone. And when we take the limit of our results when the variable x tends to positive infinity, e raised to the power minus ax overpowers everything. The result vanishes to 0. So in the first case, we have minus a times cosine of 0 is 1. We have a over a squared plus b squared. And in the second case, again, negative a at infinite boundary overpowers. We put, for example, e into the denominator, e raised to the power ax, this time positive when x grows without bound. This function outpaces, the growth of that function outpaces all this bound trigonometric functions, so it becomes 0, minus b times cosine is 0. Again, cosine of 0 is 1, minus times minus plus b, so there we go, b over a squared plus b squared. Again, remember these results. I will be referring to these here results a lot. Commit this episode to memory and these results to memory, how we obtain them. This is all trivial manipulation, not that difficult. Remember the constraint here for the integrals to converge, for the improper integrals to converge. In this case, a must be greater than 0. I showed it in red. A must be greater than 0. I showed this in red. And we put minus sign and minus sign in front of a in both cases. But wait, this is not it. There is more. If you understood what just transpired and the mechanics of how we obtain the results for the two given indefinite integrals, then you should be able to evaluate the two integrals shown on the bottom in light green here and here on your own, with the added constraint over here that not only the real number a, the real number p in both cases, I will say right here, a and p both must be strictly larger than 0. I will not tell you what the results of these problems are. We will actually have this problem on this channel. We will solve it in the near future. But the integrals over here are quite similar to the ones that we see here, here, and here, and here, with the exception that, for example, with respect to the convergent improper integrals, here we add one more factor into the structure of the integrands, and that one more factor is x raised to the power p minus 1 in both cases, when the trigonometric function of cosine makes its way into the integrand, and when the trigonometric function of sine makes its way into the integrand, x raised to the power p minus 1. If you understood, these results will be needed when you solve this problem. Ready, set, go. Wonderful. The indoctrinated members of our audience already know that first and foremost, mathematics is an art, form of telling a story, of how and why. And in order to tell that beautiful story of how and why, we need to precisely exhibit our creativity, ingenuity, and improvisational skills. And in what about to transpire next, I will try to make it as a fun, lightweight exercise. Try to think on your own what is mathematics with a capital M and what is not mathematics with a capital M. And the hint or a spoiler alert, it is not integration by parts, even though this is the first thing that we will do. Let's write down our first integral. Which one is it? It was the integral for the cosine C. I will omit the sub-indexes a and b and designation it as a function of x, where we'll understand what is going on. The real estate size is limited, so I will use this compact notation over here. So we will write it as follows. What was it? It was the cosine. So cosine bx, and we put our exponent under the differential. You see, this is the maneuver. 1 over a actually lives under the exponent. We put all this mass under the differential. This is an equivalent transformation, but what we did here is we prepared our locally available material for the construction of a system of linear equations in the given integrals. And we do so first by, yes, admittedly, u dv is equal to product uv. So that will be e to the power ax times cosine bx divided by a minus integral of v du. So in this case, v is our 1 over a integral e to the power ax. You see, this is the wonderful property of the exponential function times du. The first differential of the trigonometric function of cosine is negative sine. So this becomes plus, because we have a composite function, times the derivative, first derivative or first differential of this guy, which is b. So now we have b over a times sine bx dx. And what is this animal right here? I will use a different color chalk over here. And what is this? This is precisely our integral s. You see, this is our integral s. And if we repeat the same maneuver for our integral s, this is e to the power ax, but we move this whole thing right away. Let's do this on the fly. Save a little bit of space. So this will be 1 over a integral of sine bx d e over ax. Again, u dv is equal to uv minus v du, integral of. So we have e to the power ax times sine, this time, of bx divided by a minus 1 over a. And this time, let's write this integral right away in a different color so you don't understand, so you understand what is going on. Integral of this function v, which is e to the power ax times du. So what is the first differential of the sine? It is cosine of bx dx times the first derivative of bx, which is what? B, exactly. So now we have b. So what is going on now? Well, you should recognize this again as our integral c. And what do we have now? Now we have a system of linear equations that looks as follows. C is e to the power of ax times cosine bx divided by a plus b over a s, and s is e to the power ax times sine bx over a minus b over a c. You see, this is how these things work. Now, as a spoiler alert, this is the end of mathematics with a capital M. This is the end of us acting in the capacity of a professional mathematician, let's say, or a person who puts his or her mind into the mode of thinking like a mathematician. This is the end of mathematics. This is the idea. What follows next is not mathematics. What follows next is basically computational calisthenics, if you will. This was the idea. This is the time that we spent thinking about the solution of this problem and acting in the capacity of a mathematically oriented thinker. What follows next is just baby computational calisthenics. So let's carry out these computations together. It's not really nothing complicated. My idea is just brute force. Take the right hand side image of S and slug it into over here, because then we have nothing but the material that contains C. Game over. We see that conceptually problem is solved. So let's roll through this. So we have e to the power ax divided by a times cosine bx plus b over what? A squared, right? B over a squared e to the power ax times sine bx minus b squared over a squared c. Okay, this maneuver is understood by everyone, nothing complicated. So what do we do now? We have c on the left hand side, c on the right hand side, collect everything. So what do we have, let's say, on the left hand side? We factor this guy out right away. We brought this in, factored out 1 plus b squared over a squared. So this will be a squared plus b squared over a squared. And this, all this mess is equal to, let's do this, e to the power ax can already be carried out right away, factored out. And what do we have here? Here we have cosine bx over a on the right hand side plus b times sine bx over a squared. This is already nicely a squared, already nicely over here. So what's left to do? Well, we need to bring all these beautiful animals over here under the common denominator, a squared and a in front. And what do we see? Well, this is now trivial. Look, we multiply both sides of this equation by the reciprocal of this guy right here, flip him. A squared goes into the numerator, the sum of squares into the denominator, but a squared over here, what? Cancels out. Exactly. So now we have right away the integral c is equal to, let's write it down in this format, a to the power of ax times a times cosine bx plus b times sine bx divided by a squared plus b squared, and for the pedantic members of our audience, plus a constant of integration c to designate the cosine. Game over. One more time, just to impress it onto the minds of our viewers. This is creativity, ingenuity, and improvisation. By combining, this time you see it's not just the blind and boring integration by parts all the way through. No, when you combine things, that's when interest arises. And this is exactly what we did. Mathematics, whatever followed after that, not mathematics, computational calisthenics, but the result already agrees with what we obtained previously. On the one hand, what follows next should be left as an exercise to the viewer, and on the other hand, based on my experience of writing on Quora, for example, people of all sorts of walks of life come to this material, and they also have different level of mathematical maturity and mathematical preparedness. So in order to make sure that everyone in the audience understands where the next maneuver come from, we show these baby steps that you're expected to carry out on your own explicitly on the board. I already pre-wrote some of these results. Basically, once we have the expression for C, in some sense, this is an abstract, if you will, linear algebra problem. We have two equations, two unknowns. Everything is well defined. What these objects, C and S, are, nobody cares at that point. And once you have the answer for C, you simply take it and blindly insert it over here for the expression for S. You see, so you put the first term, this guy goes up to here, minus b over a multiplied by this expression. We throw out the constant temporarily. So this is the expression. And what do we do here? Well, look at this. We already have the parameter a in the denominator in both cases. So what's missing for the common denominator? The sum of squares, a squared plus b squared. So we slug it in over here, multiply the numerator of this here sign by that number, and put it into the denominator. So here, e raised to the power ax over a and over a squared plus b squared is the same factor. We factor it out, take it out. And what remains? Well, what remains is the sine of bx multiplied by this sum of squares. A squared sine, b squared sine with a plus sign, minus b that runs through the numerator and bumps everybody in its way. AB times the cosine, AB times the cosine with the minus sign, minus b squared. So what do we see now? Well, what we see now is the following. The sine with the b squared and sine with the b squared cancels out. Wonderful. And here we have, look at this. We have one copy of a in the denominator. This copy enters into a passionate love affair with this factor right here, a. So square is gone, and this copy gone, erased. So what do we have in the end? Let's collect everything into one convenient expression. We have e raised to the power ax times what's left over here. You see, our favorite constant a is bound to the trigonometric function of sine this time. So we have a times sine bx. And what do we have here? We'll have negative b. So minus b times cosine bx divided by our sum of squares, a squared plus b squared. And we throw the integration constant c with a subscript s to designate our favorite trigonometric function of sine, and voila, we have our results. The result for the sine, the result for the cosine, in agreement with the previously obtained results. Observe that in the previous evaluation of the given integrals, we started our solution with a boring step, the step of integration by parts, but then we knew better when to cut our losses, stop this boredom, and cleverly construct a system of linear equations in the given integrals. In this third and final creative evaluation of the given integrals, we will channel our creativity in a totally different direction, and we will show that actually both of these integrals honor one and the same homogeneous linear ordinary differential equation with constant real coefficients. And the point of this exercise is twofold. First, we want to underscore that the integral part of the fabric of studying mathematics should be this particular process of fixing a given problem and then generating as many different enough solutions to this problem as possible, with the converse task, of course, is finding a method or some sort of machinery that can eat multiple distinct problems for lunch. And the second point of this exercise is to show that while you most likely will fail to do the right thing on the first go, no one does. We all learn how to do this, but the idea is to strive to turn your solution of any problem in mathematics, theoretical physics, or computer science into a work of art, or a miniature work of art. That's right, extra credit to every student who managed to name not only the author of this work of art, but the work of art, the name of the work of art itself. So here we step as follows. Remember that by definition, if a function f of x, let's say f of x, has an antiderivative, then we capture that fact as follows. The function uppercase f of x must be at least once differentiable, and its first derivative with respect to its independent argument precisely recovers the shape of the given function f of x. And in the integral notation, we write this as follows. The indefinite integral of f of x dx is equal to f of x plus a constant of integration c. So now imagine that instead of f of x, here, let's say we have our favorite function. Let's say we start with the first one with the cosine e to the power ax times the cosine of bx. What does it mean? It means that if we take the first derivative of both sides, this becomes the function f of x. This is our guy, and this becomes what? This becomes the first derivative of the mystery, not known to us yet, antiderivative of this here function, where we have the trigonometric function of cosine. Now, the interesting part over here is the following. By the time students take on integral calculus and start fiddling with indefinite, definite, proper, improper, and contour integrals in the complex plane, they all know this basic material, all know this. Boring in some sense, definitions, yada yada, who cares, what else is new? However, the question is, and it comes down to the crux of the matter of human creativity, why, oh why, do virtually none of the students are capable of generating the idea, or why most of the students fail to generate this idea? Well, let's see how this idea can be spun creatively into a tangible result. So we write down our expression for the function for the first one. It doesn't really matter which one we start with. For the trigonometric function of sine, it will be the same result, but here we'll start with the cosine dx. We boldly assume that our function does possess an antiderivative, and we say that this is how we capture this. Now, because I have a limited amount of real estate, in order to save on that real estate and save us some time and make things easier on the eye, we will basically write this notation as follows. The first derivative over x of the function, uppercase f, will be this. In the parentheses, the number, first derivative. This is a much more scalable notation than all other ones because, for example, instead of writing 17 primes and basically making a mistake in this, we can write f paren 17, game over, 17th derivative. So the number in the parentheses in the superscript over the function represents this blah derivative. Now we use this right away as follows. We take the first derivative of both sides of this equation, the first derivative of the left-hand side and the first derivative of the right-hand side. What do we have on the left-hand side? Well, this is a composite function, so the derivative of the exponential function will be what? It will be a times e raised to the power ax times cosine bx minus the first derivative of cosine bx, so it will be b e raised to the power ax times sine of bx, and this is equal to the second derivative. You see, the first derivative of the first derivative is the second derivative, and right away we use this expression, this relation, let's say, to capture this guy, the monkey in the middle. So from here we write down the following: minus b raised times e raised to the power ax times sine bx is equal to second derivative minus, we carry this over, what is this? A times this animal, but this animal is our first derivative, so minus a times first derivative. You see, this is how these things work. This maneuver should be understood by literally everyone because, again, this expression over here is none other then this, you see, the first derivative. So this is f, in some sense, if it's easier for you to work with prime, so f prime is this. Carry this over and keep the minus sign over here. So minus b times e raised to the power ax times the sine bx is the second derivative of the mystery to be uncovered antiderivative times minus a times the first derivative. That's it. That's very straightforward. Now we repeat the whole thing again. We take the first derivative of the left-hand side of this expression and the first derivative of this. So here we get the third derivative, evidently, and we will have what? By the looks of it, two more 4 terms over here. So let's write this down. The first derivative of this composite function will be a squared times e raised to the power ax times cosine of bx, and then the first derivative of cosine of bx, so it will be minus ab e raised to the power ax times sine bx. You see, this is why we expressed this minus negative b times this guy right here. Now let's do this guy. You see, here the first derivative of this function will be, again, a comes down, ab with a minus sign, and the whole thing. So this guy, so this will be what? This will be 2 of these terms. And minus, by the looks of it, what? B squared e raised to the power ax times what? The cosine of bx, and that is equal to the third derivative. This is the third derivative of f. The first derivative of the second derivative is the third derivative. Wonderful. Now what we do is we go back to our initial relation over here and this here relation, and we bring all this material on to the left hand side. So again, if that is easier for you, let's do this. E times e, like our exponent, times the cosine is what? This is, again, f, the first derivative. This guy, minus 2, this, we already know with the negative sign. We know what that is. This expression is shown over here. So this will be, let's do this. Don't forget that we have the minus sign, so it will be plus 2f second derivative plus, so this will be actually minus 2af prime 1, like this. And what is this? Look at this. This is another first derivative of f. Game over. This is not complicated material. This is just, again, comes down to the idea of creativity and ingenuity. The manipulations themselves are not complicated. It's generating the idea. That's where the challenge is, and that is precisely during that time we act on the capacity of a professional mathematician, or we think like a mathematician. So when we bring everything together, what do we have? Let's do this. We have a square, the first derivative, minus, this is minus with this, plus 2f prime, like this, times a, and this a meets another 2a, so we have minus 2a square f1 minus b square, the first derivative, equals to the third derivative. You see, this is very straightforward, nothing really complicated. Now let's do a little bit of baby arithmetic. Look at this. The first derivative of f scaled by a square shows up over here. So this and this becomes what? Let's write it down. Let's write it down right here. So we have 2af second derivative, this guy. So when a square f first derivative and minus 2a square first derivative of f collide, negative a square survives. f1 minus, we have another b square over here, b square f prime equals to the third derivative. You see, game over. We can bring in these two terms together and put everything onto one side of the equal sign. Let's do this. So we have the third derivative of f, right? This one jumps over the equal sign with the minus sign to a f second derivative. When we take out minus, a squared becomes paired up with b squared with the plus sign, and when the minus jumps over the equal sign, it becomes plus, so it will be plus a squared plus b squared, first derivative of f, and all this beauty becomes 0. So this is what's called a homogeneous, because the right hand side is equal to 0. Linear, because all the derivatives are in the first power. Ordinary, because the differentials are full or complete, dx. There is no partial derivatives equation. With constant real coefficient 1, negative 2a, a squared plus b squared. This is a constant, and every such constant is a real number. So now, once we obtained this equation over here, we let the mighty theory of differential equations take over, and we solve this differential equation by the book. If in your journey you manage to get this far, then it is expected that you know at least a little bit of something about the theory of ordinary differential equations. You've done your fair share of existence and uniqueness theorems, linear independence, the sum of linearly independent solutions, partial solutions, and so on. So here, instead of solving this equation by hand, we will see the entire might of the theory of ordinary differential equations. We'll take a shortcut, a purely utilitarian approach, because this is what most likely you will do in the capacity, if you act in the capacity of a research mathematician or a physicist. You will be working fast and furious. You want the result at this point. You don't want to be fiddling with these things by hand. So the way these things work, again, in lightning round, usually we construct the one exponential function, and we think that this is a solution. Then once we insert this exponential function into the equation, it is satisfied. We construct the so-called, as a result, we show that we have a product of two things. One thing cannot be null, cannot be zero, then the other thing has to be zero. That other thing will be a so-called characteristic polynomial, and the characteristic equation then will be when the characteristic polynomial is equated to 0. So in this case, the characteristic equation will be what? It will be, let's say, lambda cubed minus 2a lambda squared by the order of the derivative over here second, plus a squared plus b squared lambda, and that is equal to 0. And now we try to solve this equation. If this equation is fully fledged cubic equation, then there is some pain along the way, but this time there is no pain. It's the factorization of this polynomial is quite merciful. We have the following result. Let's see, lambda times, and then lambda squared minus 2a lambda plus a squared plus b squared is equal to 0. And that means that we have what? We have 3 roots for this equation, and the first root, lambda 1, will be 0, and the next 2 roots, lambda 2, 3, let's see if we can write these roots down right away. Minus 2a, and then we, for the first part of the root, we take this factor with the negative sign. It will be 2a. Minus 1 times minus 1 is plus 1, divided by 2, so it will be a. So we write down a right away, plus minus. What will be for the, what will we have under the square root? Well, it will be this guy squared, 4a squared. So maybe let's do this, 4a squared minus 4 copies of the most senior coefficient times this guy. So minus 4a squared minus 4b squared. So a squared will cancel out. Square root of 4 will be 2. There's another 2 in the denominator, gone. Square root of negative 1 is I. And look at this, how beautiful these things come out to play. Minus I times B. We'll understand where this came from. And now there is this exciting time to write down a general form of the function that is solution of this here homogeneous linear ordinary differential equation with constant real coefficients. Precisely because of this constant real coefficients, we know that usually when there is roots with certain multiplicity involved, we will be piling on terms that look like this: C1 plus C2 times x plus C3 times x squared, and so on, cmx raised to the power m minus 1, if the multiplicity of root is m. But in our case, the multiplicity of all the roots is 1, and that means that the general solution of this equation will be the following. So the shape of f of x will be the following: the constant c1 times e raised to the power 0x, that's 1 evidently, so we already have one constant popping out right away, plus the constant c2 e raised to the power ax times the cosine of bx, plus the constant c3 times e raised to the power ax times the trigonometric function of sine bx. This is basically the output of the general theory of how these particular types of ordinary homogeneous differential equations are solved. Again, nothing complicated. This is by the book, and all that is left to do now is recover the values of the constants c1, c2, and c3. In general, as far as I'm aware, there does not exist a one standard, if you will, industrial strength algorithm for the recovery of the constants of integration. And again, in general, if nothing else is said, this is the best we can do. We leave our the shape and the structure of the function that solves the given differential equation in that form: constant C1, constant C2, constant C3. If we're given some sort of initial conditions, then we can perhaps, and if we have enough of those, then yes, we can slug in these initial conditions into all sorts of things and try to recover the synonyms for, or the actual names for, the constants of integration. In physics, for example, quite often we can tend, for example, if the exponents over here are negative, we can tend the argument, due to the nature of the physics of the problem, to, let's say, positive infinity, and then once the positive infinity takes over, the exponents vanish, taking with them into oblivion the constants. Something can be said about the structure, what's on the left hand side, and so on. We can play these games, but in this case we can actually do much better than just walking away from this expression. Why? Because we precisely know the shape of the first derivative f prime. In some sense, this is what we started with, and now all we have to do is write down two expressions for this first derivative. This is what we started from, and this is what we obtained. And we know how to compute first derivatives. We compute the first derivative of this expression, designated with this arrow. I did not want to insult your intelligence. You know how to do it. This is a typical, in some sense, let's say, middle school activity. We know the shape of the function. We differentiate it over x once. Vanishes. Here we have two terms. Here we have two terms. Four terms in together. 1, 2, 3, 4. Wonderful. And what do we do now? Well, now we take what we have against and juxtapose it. What we need. This is what we need. This is what we have. And from this we draw the conclusions. The constant of integration C1 is by itself, but in some sense this is what we expect. The antiderivative is blah blah substantial plus the constant of integration. Boom, we have it free of charge. Now the remaining two constants, C2 and C3, we can recover. Why is that? Well, look at the shape of the first derivative. In this derivative, in the first derivative, in some sense, only the trigonometric function of cosine is present, or in some sense here in this land, it means that only the trigonometric function of cosine survives. The trigonometric function of sine packs its things and goes home. What does that mean? Well, that means that, let's write this down over here. I'll suggestively write it in different colors so you understand where did it come from. E to the power ax cosine, this is the signature over here, so a times c2, and we crawl through this expression and we see, okay, sine throw out, oh, look at this, cosine, so plus b times c3 must be what? What is the coefficient in front of this animal in the actual first derivative? It's 1. So it's 1. Wonderful. So we have it. And now we do the same thing. No signs, so we roll through this expression and we throw out every sign. So what do we have? We have, let's say, b times c2 with the minus sign, but we flip it into the plus sign, so this guy will be minus a c3 must be 0, you understand, right? Originally it will be minus b times c2 plus a c3 equals 0, but multiply through by 0 and obtain this. This is cosmetic change. So now that's it. Again, another system of linear equations in two variables, c2 and c3, well defined. We have enough information. We can always solve it. I will not, on the one hand, I do not want to insult your intelligence. You know how to do it. Again, once the formal, let's say, mathematics takes over, it doesn't care what these variables are. We just solve this system of linear equations, two unknown, two equations. So let's do this. From this equation, let's take it this way. From here, we will jump where? Let's jump over here. So we will say that which one can we recover? We can recover, for example, C2. So we say that A C3 is equal to B times C2, right? We carry this guy on the other side of the equal sign. A times C3 equals B times C2. So C3 is equal to B divided by A times C2. You see this deduction from here, we get this. Now we take this guy, its right-hand side portrait, and slug it into here. So what do we have? Let's write it down. A times C2 plus B squared over A times C2. C2 is equal to 1. You see, this is it. So what do we do now? We multiply this expression, this relation through by one copy of A, and we obtain A squared times C2 plus B squared times C2 is equal to A, right? A and A cancel each other out, game over, carry this out, so what do we have? C2 times A squared plus B squared is equal to A. And from here, it follows that for C2, let's write this down, C2 is equal to A divided by A squared plus B squared. And because we are the smart bears right now, we remember, what is this guy? Turns out that this constant comes out to be numerically equal to the improper integral, remember? Improper integral from 0 to positive infinity e to the power of minus ax times cosine bx dx, but this is just a random mathematical butterfly, if you will. We know the value of the constant c2, and what do we do now? Well, we use this expression right here, and into this expression we put the right hand side of this expression. And that is a trivial thing to do. Look, we have our constant C3 is basically the constant C2 scaled by the factor of B over A. So if we multiply this ratio by B over A and A in the numerator and A in the denominator will cancel out. And what will we have for C3? Exactly, it will be B over A squared plus b squared. And as yet another random mathematical butterfly, you know that numerically this is equal to the same improper integral, but this time e raised to the power minus ex. So this time the integrand will contain the trigonometric function of sine bx dx. This will be another ubiquitous result. But anyway, now that we have the shape of both constants, we write down, I took the liberty to move this expression over here so we can write down the following result. Remember, so what did we have before? Technically, okay, pedantically, we had c a b of x. This is our integral. This is what we called fx. And this is our integral e raised to the power ax times cosine of bx dx. Now we just write these things down. Okay, c1 plus the denominator in both constants is one and the same, the sum of squares. And we have the same exponent, e raised to the power ax is the same. So we again group these terms as follows: e raised to the power of x times. But this time we just need to be careful about c2. A is bound to the trigonometric function of cosine. A times cosine bx plus, what is the constant c3? C3 is bound to the sine, so b sine bx divided by the sum of squares. And voila, we have our constant of integration. Identically, we can even probably replace it with something else, something more specific for the our integrand over the cosine, because I will not be doing this in a public setting. I will leave it as a fun exercise to the viewer. You should prove to yourself that if you start with the following expression, let's say it will be e raised to the power ax times sine of bx equals to your antiderivative f of x with the taken with the first derivative, then you will come up, you will construct exactly the same differential equation. It will have exactly the same structure. You will have f1, 2, 3 minus 2a f1, 2 plus a square plus b square f prime equal to 0. The structure of the differential equation will be exactly the same even in this case. Prove it to yourself. I will not be doing it. This is a fun exercise for you. So what gives in this case? Okay, what gives in this case is the structure of the constants of integration. You will have the same characteristic equation. The roots will be the same, but when you will be writing down the conditions for your constants, then it will be a different story, because now you will, once you take this first derivative of f, your antiderivative, the first derivative of it, you will see that in the original function, where is it? Right here. You will have, instead of cosines, you will have the sine. The sine has to survive. So this will have to survive, and this will have to survive. You see, instead of being 0, now it will be what? It will be 1, and this will be 0. So once you solve this system of linear equations for C2 and C3, boom, you will have your constants and the corresponding result. Game over. So like I said before, the two purposes of these exercises is to show, on the one hand, that fixing a problem and coming up with as many distinct solutions to the problem should be an integral fabric of studying mathematics, because this is how we develop our ingenuity and creativity. This is only, let's say, global or strategic sense, but in a tactical sense, the reason I wanted to go through this exercise with you again one more time is, remember, in season 1, episode 1, in the very first episode on this channel, I shared with you the fact that sometimes I stick my fingers into raw clay, then my art instructor fires raw clay in a kiln, and let's say a work of art, let's say a sculpture comes out, boom, here we have it. Well, here in mathematics, the idea is exactly the same. The local material that you have is your raw clay. and you sculpt it into the needed result, any which legal and mathematically valid way possible. In other words, my suggestion to you is not to do not stick to the mud, so to speak. Do not think that if you're doing integration, oh my God, there is only one way to do these things. No, this is not the case. There is no codified set of rules in Greater Beyond that says, thou shalt only solve integral calculus problems this way. This is not the case. There is no such codified law. You can treat all these mathematical material precisely as your raw clay and then sculpt it into the final result in any which mathematically legal way possible. In the first case, we took our raw clay and we sculpted it into the complex numbers. We brought in this complex numbers. Remember the Euler's formula. In the second way, we sculpted our way through system of linear equations. And in the third way, yet we took our raw clay and we sculpted it into the result through the homogeneous linear ordinary differential equation with constant real coefficients. And perhaps there is yet another and maybe yet another and another creative way to evaluate these two integrals. If you come up with them and your ideas are different from mine, then I'm all ears. I'm always eager to learn new things and hear from you what is your beautiful, crisp, and elegant idea. Now, this is it for the mathematical problem S3E24, and we will move on to a new challenge next. Our next problem will be yet another problem in mathematics, S3E14 this time. And in this problem, we're asked to construct a divisible by 7 algorithm. In other words, we are asked to come up with a finite procedure that takes in as an input a number. Let's say we're interested in a whole, evidently, positive number, and then in a finite number of steps, it produces the answer, yes, this number is divisible by 7. And alternatively, it says, no, it's not divisible by 7. So 7 is the number. 7. Think about what is so special about 7. Do it on your own as a hint. If you cannot do it, then as a hint, my solution, my algorithm that I will discuss in the next episode is based on the so-called scope reduction problem solving approach, or if you will, reduce and conquer. One more time, if you joined our channel after season 2, then you actually missed out on a lot of good material across seasons 1 and season 2. We studied all popular problem solving approaches in a dedicated manner. A block of episodes dedicated to this particular problem solving approach, reduce and conquer or scope reduction. We studied this problem solving approach across season 2 episodes 21, 22, 23, and 24. The easiest way to find these episodes on this channel is to use the season guide, season 2 guide. Pop it open in the separate tab in your browser. This PDF file is absolutely free of charge. In all these season guides, I index all the episodes that we have on this channel. Scroll down, find these episodes, click, watch, work your way through, and hopefully construct an algorithm that will decide whether a given input, let's say whole positive number, is divisible by 7 or not. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my algorithm for deciding whether a given input whole positive number is divisible by 7 or not. Yeah.